At the Department of Aeronautics at Imperial College, London, the third-year applications task is to design a runway-launched gliding robot that weighs less than 70 grams and fits into a 50-centimeter diameter.
I'm Lockie, and I'll be showcasing my group's approach to this task. We began by researching low Reynolds number flight.
We didn't use all the information we gathered, but it guided us towards some initial design decisions. To realize these, we split into teams. Devesh and Sanjay were responsible for computer-aided design. Brian and Yu Chan did our mathematical modeling and programming. Chema and Anu conducted structural analysis and reporting, while Melissa and I were responsible for administration and creating our assessment videos. Once we had our first CAD model, we headed into the workshop to validate some manufacturing problems we foresaw.
These lessons helped us to finalize our first iteration design, which I have here. It features a foam inverse Zimmermann planform, which is glued to two balsa ribs.
The drivetrain is attached to the ribs by squeezing two clips that attach to the base plate. Two smaller clips secure the carbon fiber wheel axles. To stop the axles from sliding, we used a small roll of Scotch tape. The motor housing is screwed directly into the base plate, and our gear ratio is 1:1.
Our design allows us to move the drivetrain longitudinally to adjust the center of gravity, and to adjust the wheel configuration. The base plate can also be flipped about any axis.
Our mathematical model showed a final flight distance of 3.7 meters. During preliminary tests, we slightly underperformed this, with flight distances between 2 and 3 meters. The problems contributing to this were an occasional turning on the runway, wheel slipping, and that the glider was overweight by about 15 grams. Also, our balsa ribs snapped during an early test flight, but we just taped them back together.
These problems drove the design changes we made for our second iteration design, which I have here. It still features the foam plate, balsa ribs, and attachment mechanism. However, the balsa ribs now have more lightning holes and different hole placement.
We also reduced the size and thickness of our drivetrain to save weight. Our motor and wheels are mounted in the same way. However, this time we laser cut some acetyl stoppers to prevent the axles from moving. We also increased the axle length from 11 centimeters to 13 centimeters for better ground stability.
We chose not to do anything about wheel slipping since we had observed during testing that ramping up torque affected our runway and velocity. Unfortunately, our second model was still slightly overweight.
So, after conducting a friction coefficient test for validation, we removed the rubber from our tires. This took our weight down to 67.44 grams. Using this new weight and friction coefficient, our mathematical model output a flight distance of 3.6 meters. Early tests of our model showed good, consistent performance, with flight distances close to those predicted. Our test day performance was a different story, however, with 4 nosedives and 1 backflip, giving us a flight distance of 1 meter. We returned to the flight arena later, and discovered that our glider performed consistently without the telemetry balls attached to the top. However, it is unclear if this is the sole reason for our poor performance.
To enhance a future design, we would aim to reduce weight again, perhaps by using 1 rib instead of 2.
We would also investigate the effects of the telemetry balls on the flight surface, and design a system for better mass placement on the drivetrain, since these seem to influence performance greatly.
Our take-home message from this project has been that despite rigorous theoretical engineering, you can't completely account for field conditions. Sometimes, performance is just down to luck.